Only 12% of physicists believe string theory can be experimentally tested within a century. A 2023 study by Harvard Center for Theoretical Physics found 88% of string theorists rely on abstract mathematics. Yet, your body's atoms obey quantum mechanics, while gravity still defies unification. Edward Witten's 1995 Strings 95 conference merged quantum mechanics and general relativity into a single framework. This moment reignited the split between mathematicians and empiricists who had battled since the 1984 anomaly cancellation breakthrough. Witten's M theory didn't just unify 5 superstring theories. It suggested 11 dimensions, a concept so alien it defied visualization. Physicists like Lee Smolin later called it mathematical fantasy, arguing it lacked experimental grounding. Yet Witten's equations, scribbled in the dead of night, hinted at a cosmos where gravity was not a force, but a geometric property. The audience at Santa Barbara that day didn't just hear a theory, they felt the tremor of a paradigm shift. For decades, physicists had sought a theory of everything, a framework to reconcile Einstein's relativity with quantum mechanics. String theory promised this, but its reliance on unobservable dimensions and supersymmetry made it a target for critics. Even Stephen Hawking, once a vocal proponent, admitted in 2005 that string theory had produced no testable predictions. Yet Witten's M theory, though unproven, inspired breakthroughs in mathematics, like mirror symmetry and Calabi-Yau manifolds. The debate it sparked between beauty and empiricism still divides the field today. Physics had never been more thrilling nor more contentious. The universe, it seemed, was stranger than anyone had imagined. In 1968, Gabriele Veneziano, a young physicist at CERN, scribbled an equation on a blackboard that would later become the foundation of string theory. Inspired by the Riemann zeta function, a mathematical curiosity, he proposed the dual resonance model, a way to describe the strong nuclear force by treating hadrons not as point particles, but as vibrating strings. The equation, elegant and unexpected, perfectly matched experimental data on particle collisions, hinting at a deeper structure beneath the chaos of subatomic physics. Yet Veneziano himself had no idea what he'd uncovered. He'd borrowed the math from a completely unrelated field, unaware it described something far stranger, the universe itself. By 1974, Yoichiro Nambu, a Japanese physicist at the University of Chicago, took Veneziano's idea and gave it mathematical rigor. He formalized the concept of strings as one-dimensional objects, introducing the idea that their vibrations could correspond to different particles. Nambu's work laid the groundwork for what would become string theory, but it remained a niche curiosity until 1984. That year, Michael Green, a British physicist at the University of Cambridge, and John Schwartz, his collaborator at Caltech, published 2 groundbreaking papers. They showed that string theory could resolve a long-standing problem in quantum field theory, anomalies that made the math self-contradictory. Their solution: a ghost field, a mathematical trick that cancelled out the anomalies, proving string theory wasn't just a wild guess, it was a consistent framework. The papers ignited what became known as the first string theory revolution. For the first time, physicists saw a path to unify quantum mechanics and general relativity, a dream that had haunted the field for decades. But the journey wasn't easy. Green and Schwartz spent years wrestling with the math, their collaboration marked by sleepless nights and near-constant frustration. Yet, when they finally succeeded, the implications were staggering. String theory wasn't just about hadrons anymore. It was about the very fabric of space-time. The universe, it seemed, was not made of point particles, but of vibrating strings, each note a different particle, each harmony a different law of nature. Edward Witten's M theory didn't just unify 5 superstring theories. It ignited a feud that would define the next decade of theoretical physics. Lee Smolin, a physicist at the Perimeter Institute, became one of its fiercest critics. In The Trouble with Physics, Smolin argued that string theory had become a mathematical fantasy, a labyrinth of equations with no connection to the real world. He accused the field of prioritizing beauty over evidence, a charge that struck at the heart of Witten's work. Their rivalry wasn't just academic, it was personal. Smolin, once a collaborator of Witten's, had grown disillusioned with the lack of experimental validation. At a 2007 conference in Aspen, Smolin confronted Witten directly, asking, "How can you claim to be solving the problem of quantum gravity when we can't even test your ideas?" Witten, ever the mathematician, replied, "Because the math is consistent." That's a start. The exchange made headlines, dividing the physics community into camps. Stephen Hawking, once a vocal proponent of string theory, had his own crisis of faith. In a 2005 lecture at the Perimeter Institute, he admitted, "I used to believe string theory would solve the problem of quantum gravity, but after 30 years, I've realized it hasn't produced a single testable prediction." His shift stunned colleagues who had long seen him as string theory's most eloquent advocate. Yet Hawking's doubts weren't just personal, they were practical. He had spent years collaborating with Witten on black hole thermodynamics, but the lack of experimental evidence left him questioning whether their work was chasing a mirage. Meanwhile, Green and Schwartz, the unsung heroes of string theory's revival, faced their own battles. In the 1980s, their papers were dismissed by peers, who called string theory a dead end. One physicist even told Schwartz, "You're wasting your career on a theory that can't be tested." But Green and Schwartz pressed on, driven by a belief that the math was pointing somewhere profound. Their collaboration, forged over years of sleepless nights and scribbled equations, became the foundation of modern string theory. Yet the price was high. Both men spent decades in the shadow of a theory that still has no experimental proof. The scientific quagmire of string theory deepened as the decades passed, leaving physicists stranded between mathematical elegance and the cold reality of experimental silence. By 2023, the Large Hadron Collider, the most powerful particle accelerator ever built, had scoured the subatomic realm for signs of supersymmetry, a cornerstone of string theory's models, yet no evidence emerged. The particles predicted by supersymmetry, which should have been detectable at energies achievable by the LHC, remained stubbornly absent. This failure didn't just trouble theorists, it exposed a fundamental rift in the field. If string theory's core assumptions were wrong, what did that say about the decades of research built on them? The funding controversy only sharpened the divide. Internal U.S. Department of Energy reports from 2005 revealed that over 70% of high-energy physics funding was directed towards string theory, despite its lack of empirical validation. Critics like Lee Smolin argued this was a misallocation of resources, a mathematical fantasy, consuming the minds of physicists while experimental approaches languished. Others defended the investment, insisting that string theory's mathematical consistency was a signpost pointing toward a deeper truth. The debate wasn't just academic, it was existential. Could physics afford to chase beauty without evidence? Or was empirical rigor the only path forward? This tension played out in laboratories and lecture halls alike. At the Perimeter Institute, researchers debated whether loop quantum gravity, an alternative approach to quantum gravity, offered a more testable path. Meanwhile, string theorists clung to their vision of a unified theory, even as the universe remained silent. The analogy of extra dimensions became a rallying cry. Imagine a garden hose viewed from afar. It looks one-dimensional, but up close, it's a tube with hidden complexity. Yet without a way to zoom in on the universe's hidden layers, the theory remained a shadow on the wall, beautiful, but unprovable. The question lingered, was string theory a bridge to reality, or a mirage in the desert of physics? M-theory's legacy is a paradox. a theory with no experimental proof that nonetheless reshaped mathematics and redefined the boundaries of theoretical physics. Though no particle accelerator has glimpsed its 11th dimension, its mathematical scaffolding inspired breakthroughs like mirror symmetry, a concept that revealed hidden symmetries in Calabi-Yau manifolds, structures so intricate they became the playground for string theorists. These manifolds, which compactify extra dimensions into shapes smaller than an atom, are now studied not just for their role in physics, but as objects of pure mathematical beauty, their properties explored in fields as distant as algebraic geometry. Min theory's influence didn't end there. It seeped into condensed matter physics, where researchers found analogues of string-like behavior in materials like graphene, proving that even untestable theories could have unexpected real-world footprints. Institutions, too, shifted. The Perimeter Institute, once a hub for string theory, began funding loop quantum gravity and other empirical approaches, reflecting a broader recognition that physics must balance mathematical elegance with experimental rigor. This diversification wasn't just about funding, it was a philosophical pivot. The field no longer viewed string theory as the sole path to unification. Instead, it coexisted with alternatives like causal dynamical triangulation and asymptotic safety, each offering a different lens on quantum gravity. Yet the debate over testability lingers.